Hello everyone, I'm Liu Chang, a PhD student from Peking University. Thank the organizer for giving me this opportunity to talk about our recent work based on this paper. First, I'll talk about the background about BNS early warnings, then introduce our observing strategy of realistic detection using Decihertz detectors. Finally, show the results of Decihertz detection rate and early warning parameter distributions. More content about impact of population models and confusion noise could be found in our paper. We know that BNS mergers will generate various types of EM signals. Early warnings from GW signals are thus very important for the preparation of follow-up observations. There are many studies exploring the early warning ability of the third-generation ground-based detectors, such as this one by Nitz and Canton. From their work, we see that 3D detectors have an early warning time of about hours. But to obtain a localization area of degree level, one has to wait until minutes before the final merge. We wonder, can space-based Decihertz detectors perform better, and how much better? From this plot, we see that signals could stay in the Decihertz detectors for years, which leads to a much longer early warning time. And so we calculate this TE for several systems using these four proposed Decihertz projects. This plot shows the localization precision as a function of GW frequency, which also means the early warning time. The dashed lines show the trend of using one specific detector alone, and the solid lines show the result of joint Decihertz ET detection. Notice that using space-based detector alone could already obtain a stable localization area in the last few days of the observation. With the joining of ET, it will get better by about one order of magnitude. One important message from this plot is that Decihertz detector alone have an early warning time of about days, which is adequate for EM follow-up preparations. But this was just for one system. We then carry out a further examination to explore a bunch of BNS systems, a population. We found that whether we end the observation at the merger point or one day before the merger hardly affect the detection rate and parameter precision. This plot just shows the measurement of time of merger accuracy (Tc) and localization precision (omega). We notice little difference between them. This property is an advantage of Decihertz detectors. And until now, we seem to conclude that the early warnings from Decihertz GW detector are adequate in time with accurate precision. But is this true for all the detections? We then explore the realistic detection and found some exceptions. Unlike ground-based detectors, where the signal is very short and the mission lifetime is very long, so they won't affect each other, so the detection rate will be the same. But the space-based detectors are different. They have many time scales, and most of them are in the same order of magnitude. Except for the early warning time we just discussed, the most important one is the observation time, TOBS, which means how much time the signal is in the detector. It is determined by the source merger time, TC node, and the mission time, T mission, which we conservatively set as 4 years. The detection rate and parameter accuracy then depend on TOBS, therefore on TC node and T mission. For example, at the beginning of the operation, the detection rates will be fewer and the accuracies will be worse, since TOBS is short. This timeline shows the source merger time, TC node. It starts from the beginning of the mission and lasts to infinity. All the sources that merge in this timeline are possible GW candidates. Following this timeline, we calculate the detection rate and early warning parameter position. So following the timeline, the merger events will happen according to specific population models. We explore 4 of these population models. Their redshift distributions are shown in this plot, and we choose to generate sources weekly so that the time effect will stand out. Then we put this event into the detector and calculate their detection situation. These red lines are the weekly generated sources. For those SNR over 8, we claim the detection and calculate delta omega and delta Tc by Fisher matrix analysis. Based on the merger time, we classify the sources into 3 categories. Sources that merge within 1 year are called type A. Sources that merge in 1 to 4 years are called type B. Sources that only inspiral in the whole 4-year span are called type C. Their frequency ranges are marked in this illustration. For A and B, the observation time is from the start of the mission to the time GW reaches the upper cutoff frequency of the detector. For C, the observation time is set fixed to 4 years. And type C is special in that the sources will merge after the detector shuts down. So even if the detectors are not operating anymore, the legacy of source information remains valuable. Now I'll present some of our results. Taking one population model, SFR14, as an example, this plot shows the detection rate of the detector B-DECIGO. The x-axis is the source's merger time TC node. The black line shows the weekly detection rate, and the orange line shows the yearly detection rate. We have adopted the local merger rate from LBK's population paper. The result is like this. We could observe a significant increase of detection rate in the first year, and it became stable from 1 to 4 years. A few sources that merge after the mission could be detected. The latest sources could be detected by B-DECIGO as 7 years before the merger. But when compared with other Decihertz detectors, we found that all other detectors have detected sources that will merge 20 years later. The common feature is that the detection rate of type C drop quickly. The detection rate of these detectors have a large variation due to their different noise level. Note that DECIGO here could almost observe all the sources that will merge during the mission. A simple analysis taking B-DECIGO and DO conservative as an example, we see that the reason DO conservative detects fewer sources is that it has high noise level at higher frequencies. But it can detect sources that will merge dozens of years later thanks to its low noise level at lower frequencies. Therefore, the whole detection rate is a synergy among source properties, the shape of sensitivity curves, and the merger time. Now let's see the timing and localization precision distributions. This is the joint distribution of delta Tc and delta omega. We notice that type A has a dispersive distribution and badly measured Tc and delta omega. Type B stays in the most stable and accurate region. Delta omega is about 10 to the minus 2 square degrees, and delta Tc is about 0.2 seconds. The angular resolution of type C remains precise, but the timing is getting worse. Now let's see the parameter precision trend evolving with the merger type. The y-axis are delta omega, delta Tc, SNR, and redshift of the sources respectively. We see that type A's precision is gradually getting better, while type B is stable and massive in number. But for type C, delta Tc gets worse rapidly, and only nearby sources could be detected. Compared with other detectors, this trend stays the same, only the number of detections changes. This is a summary of our work and mark the characteristics of different categories on this plot. Finally, thanks for listening.